Okay, so in this problem, car starts moving rectilinearly. So rectilinearly means in the same direction, in a single direction. So first with an acceleration. Okay, so this is an acceleration. So acceleration is basically the rate of change of the magnitude of velocity. So here we are dealing with magnitude. So I'm just telling magnitude. So actually it should also include direction. So it's basically the rate of change of velocity with respect to time. So it's dv by dt. So it's represented by the letter w. Okay, 5 meter per second square. Initial velocity is 0, so initial state values are given. Then the car travels uniformly with uniform velocity, and finally decelerating, which is the opposite of, negative acceleration basically, the same rate w. So if deceleration is w, acceleration is minus w. So then it comes to a stop where the velocity essentially becomes 0. The total time of motion equals tau equal to 25 seconds is the total time taken. It's presented by tau. The average velocity, which is the total displacement by the time taken during the time, is equal to, represented by this v. Now how long does the car move? Uniformly. That is what we have to see. So okay, so in these types of cases where you have like different time periods that have different uh, values of acceleration, so in such cases, and when you have this thing of uniform the average velocity, so average velocity is nothing but the total displacement at the time taken. So wherever you have this kind of thing where you have to find the total displacement and you have varying accelerations over time, it is always better to use a graphical method, because basically for a velocity versus time curve, the area under the curve will give you the displacement. So we start by drawing the curve. So the y-axis would be the magnitude of the velocity and the x-axis would be the time, right? All right. And so initially the car starts with zero velocity and it accelerates uniformly at a rate w, which means that, so if the acceleration is constant, so just write it. So basically I'll just represent it by w. That is what is the notation. So w is equal to dv by dt. That's the slope. So if it is a constant, w is a constant initially, this means dv by dt is a constant, which means it is v, like v, the curve of v is versus t is basically a straight line, and since w is positive initially, it will be a straight line with a positive slope, so it will go something like this. All right, so let's say the time the time for which this uniform acceleration is there is say t1. All right, okay. Now from, let's say, from t1 to some t2, it goes with uniform velocity. Now after this there is a deceleration of w, which means basically an acceleration of minus w, right? So minus w is basically a negative slope. So basically the velocity, it reduces from this particular value magnitude to 0 linearly, and we know that the total time is denoted by tau. So this is basically tau, this is 0. Fine, very good. And if we consider, like, I'll just name it for convenience, and I'll just name the vertices. So A, B, yeah, this is O, C, D, E. Okay, and see, the slope is W. Here slope is minus W. Alright, so this is theta, right? So this is the angle in a straight line and the x-axis theta. This will also be theta, but in the opposite direction obviously. Alright, so uh, so your tan theta, we consider, if we consider triangle ACO, so it's obviously a right angle triangle over here. So AC ACO is basically tan theta, which is the slope, which is W. So AC, so this means AC is equal to W into CO. CO is T1, so W T1. So this means that this maximum velocity attained is W times T1. Okay, cool. So we got the maximum velocity in terms of W and T1, right? And also we know that the area under the curve, let's just use this color. Alright, area under the curve should give me the total displacement. Alright, now another way to write the displacement, let's say I call it S, divided by S. So basically the average velocity into the total time taken, which is tau. So the average velocity is the total displacement by total time taken. Fine, we have this. We already know what is V, what is given, and we already know tau. Okay, this is, so we know what is the total displacement. We have that information with us. Now we need to find out S as area under the curve. Alright, now before doing that, one more thing that is interesting is the slopes are essentially, one is W, other is minus W. So basically these two angles are theta, so AC by CO is equal to BD by DE. But we know that AC and BD are essentially equal, right? Which is basically WT1. So AC and BD cancel out. I mean, basically like CO is equal to DE. Okay, so what is CO? CO is T1. What is DE? DE is tau minus T2. Alright, so this means T1 plus T2. I'll just write the other way, you'll understand why. So it doesn't really matter. So tau is equal to T1 plus T2. Okay, so this is basically an important equation that we'll require later. Alright, so basically, and again write the AS, which is the area under the curve. So area under the curve, so it is a trapezoid. Okay, so for a trapezoid, the area is basically half times height, which is, for now I'll just write AC into the sum of the edges, which is OE plus AB. Sorry, OE plus AB. Okay, so we already know that AC, so I guess I'll write this as 1 and I'll write this as 2. Okay, sorry, I'll write this as 2. So from 1 we have AC as WT1 and OE is obviously tau and AB is T2 minus T1. Now we know that tau is equal to T1 plus T2, so half into WT1. So if we substitute tau as T1 plus T2, T1 cancels out, 2 T2 is left, 2 cancels out, it becomes W times T1 T2. But we already know sorry, I'll just write this T2, but we already know that S is V tau. V tau. Okay, and okay, so we basically have, okay, see, so from again I'll write equation 2, T1 T2 equal to tau. Okay, and T1 T2, basically from here T1 T2 gives you this average velocity V tau, magnitude of average velocity V to tau by W. Okay, so we need to find the time for which velocity is uniform, which on the graph is basically CD, which is T2 minus T1. This is what we need to find out. Okay, so we know what is T1 plus T2, we know what is T1 T2. So how to find T2 minus T1 is very simple. Okay, let's say this is A and let's say this is B. Okay, just for reference purpose, so we'll square A. So T1 plus T2 whole square is basically T1 square plus T2 square plus 2T1 T2, which will give me tau square. Alright, now T1, this becomes T1, we can rewrite it as T1 square plus T2 square minus 2T1 T2 plus 4 times T1 T2 tau square, right? This becomes, that's what we want, T1 minus T2 whole square. I mean, we need the square root of this. This becomes tau square minus 4 T1 T2. But we know from B that T1 T2 tau square minus T1 T2 is 4 times, okay, so 4 times average velocity V times tau by W. Okay, so T1 minus T2, so basically like the root over this whole thing. So I'll just take out tau square because so tau, that's how, like, that would help us match the answer. So 1 minus 4 V, so if we divide this by tau square, then tau comes in the denominator, W tau, right? This can go out of the square root as tau times a root over 1 minus 4 times the average velocity magnitude divided by W tau. So basically this is what, so of course you can substitute the values and get the final answer, but I'm leaving it at this point because basically this is what is also given in the answer part. You can check it. So it's basically tau times square root of 1 minus 4 into average velocity by W tau. So there you have it. So I would like to point out one thing, that I have written here it as T1 minus T2 whole square and I have written it as T1 minus T2. So this should be actually T2 minus T1. Okay, so the reason being that whenever I am taking a square root on both sides, so essentially whenever I take a square root, it should be, the final square root should be positive. So actually T1 minus T2 whole square and T2 minus T1 whole square would be same, but whenever I take square root, the output should be, or the square root should be positive. And obviously, since as we know t2 is greater than t1, so the square root would be t2 minus t1. So that was a mistake. I'm sorry for that. However, that's basically the time for which t2 minus t1 is the time for which there is uniform velocity. So there you have it. So yeah, thank you.